Right, this is a video on piecewise functions. And piecewise functions are functions that really have different parts of the domain. Think of your x values correspond with different output functions. Think about what you use to get your y values, right? So for piecewise functions, different parts of the domain correspond with different output functions. So we'll do an example just taking a look at how you might see one of these. So if I said given, and I said we had f of x equals, now for a piecewise function, you know, you're going to see one of these big curly braces just to define that there's different parts of the function for different parts of the domain. So f of x equals, we'll say x squared minus 1 for x less than 0, 5 when x equals 0, and 2x minus 1 for when x is greater than 0. So basically what this is doing is it's giving you a rule to use based on what your x value is. If your x is less than 0, you want to use the first part. If your x equals 0, you want to use the middle part. And if your x is greater than 0, you want to use the last part. You don't ever use all of them at the same time. You only use one part. So if I give you these and I ask you to find each of the following, if I said f of 6, remember what that really means. It means everywhere I saw an x, right, I'm going to substitute in 6, but 6 is what x is. So if I'm looking at f of 6, well, which of these intervals contains x equal to 6? Well, that would be when x is greater than 0, right, because 6 is greater than 0, so it doesn't meet the other requirements. But 6 being greater than 0 tells me to use this, so I'm going to substitute in for the x's in this function because my x is greater than 0. So we have 2 times x, which is 6, minus 1, and then we evaluate it. 2 times 6 is 12 minus 1, which equals 11. So f of 6 equals 11. You could also think of this as a point on your graph, right? The x value is 6, the y value would be 11. Similarly, but different, if I said I wanted f of 0, well, how do you find f of 0? Well, the x value we're substituting in is 0, so when x equals 0, well, now we're in this middle case, well, that's just 5. There's really nothing to substitute in. 5 is the answer because it's a constant, right? So it's telling you it's constant when x equals 0. So f of 0 equals 5, and that's the only one you use. You don't sub 0 into the other ones because that's not the rule. The rule is x equals 0. The function you use is f of x equals 5. And we'll look at one more. If I said I had f of negative 2, well, that means x is negative 2. Well, which part of this has the interval that contains negative 2? For x, well, x is less than 0 if x is negative 2, so we're using the first function, so we're substituting into here. Remember, if you're substituting for x when there's exponent on there, you got to put parentheses, so it's negative 2 squared and then minus 1. So negative 2 squared, remember you're squaring the negative as well, that's why we have the parentheses. Negative 2 squared will give us 4 minus 1, which equals 3. So f of negative 2 is equal to 3. That's like a point on the graph, negative 2 comma 3. So, you know, when you substitute in, you're really going based off of the part of the domain they're telling you about. The x values are telling you about, it tells you which function to use. We also graph these. So if I wanted to graph a piecewise function, you'd kind of do it in the same way. You approach each part of the function individually. So for example, if I said to graph f of x equals, we'll say it equals 3 for x less than or equal to 2, and x plus 5 for x greater than 2. All right, so that's a piecewise function because for different parts of the domain, it behaves differently. And really, you want to graph each piece based on what the function would look like, just restricted to that domain. So for the first part, for x is less than or equal to 2, right, the function I would be really using is f of x equals 3, which if you remember f of x, you could really call it y. So it's really the graph y equals 3. Well, what does that look like? Well, y equals 3 is a horizontal line, right, through 3 on the y-axis. But you only use that for x is less than or equal to 2. So when I go to look at this, right, and I'll put this on a grid here so we can have an easier look at what's going on. Y equals 3 would be the line that goes right through 3 here, but this is only for x is less than or equal to 2. Well, x is less than or equal to 2, so here's x equals 2, and we want that for x is less than or equal to 2, so for everything to the left of it, we're using the line y equals 3. At the point x equals 2 itself, the y value is 3. Because this has an equal to in there, right, we're going to use a closed circle, so we're going to have the point 2, 3 is included, because we have an equal to there. And the line y equals 3, well, we just said that it's going to be a line that is horizontal and going on forever in this direction. So for all the x values less than or equal to 2, y equals 3, right? When x equals 1, y equals 3. When x equals 0, y equals 3. Negative 1, 3. Negative 2, 3. So all those points form that line, but it's only for x's less than or equal to 2. Don't draw the whole line over here because those x's on the right of this are greater than 2, and we don't want to use that. And now we want to look for what happens when x is greater than 2. When x is greater than 2, they're telling us to use f of x equals x plus 5. Remember, f of x is the same as saying y equals x plus 5. Well, what does that look like? Y equals x plus 5, that's the graph for a line, right? You know that because you have x to the first power here and y to the first power. So you know it's a graph of a line. And you know that this is going to be the line y equals x plus 5 for all x's greater than 2. But you still need to figure out what happens right at 2, because since there's no equal sign in this, you know that you cannot include the x value of 2. But you need to know what happens there because, you know, there's values, you know, between 2 and 3. So you can't just start at 3. So starting at 2, right, we want to see what happens. So you always want to substitute in what happens at the point. So for x equals 2, this gives us y equals 2 plus 5, which equals 7. So you're really going to plot the point 2, 7, but you're going to use an open circle because you don't include it. There's no equal sign in here, right? So in other words, you don't include in your graph because there's no equal to on there. So looking at this, we're going to be at 2, 7, so up 1, 2, 3, 4, 5, 6, 7. So we wanted an open circle there, so 1, 2, 3, 4, 5, 6, 7. Open circle here. And then I want to graph it like I normally would for a line. In this case, I know the line is y equals x plus 5, so I know the slope is 1, right? The coefficient in front of x is 1. So when the slope is 1, that's the same as saying 1 over 1. So the change in y is going to be up 1, change in x to the right 1, and you could plot the next point like that. And you could keep going, right? Up 1, over 1. Or you could plot other points as long as you're picking things that are greater than 2. The rest of these circles are filled in. These points are filled in. They're included in your graph. Only the boundary point isn't. And the main reason is because if I was to do the vertical line test, right, this wouldn't be a function. You can't include both of these points. Otherwise, the x value of 2 would have 2 different y values that go with it. So this is my graph of f of x. This is actually, this whole thing is f of x. All right, so you have both pieces here. Keeping in mind that, you know, at the boundary, you always have to substitute it into your function. You include the point if there's an equal sign. You put and you put a closed circle. You put an open circle, right, if you don't include the point like we did here. But then all the points after that are included. You couldn't just start this at 3 because there are values between 2 and 3 where the graph exists. Let's take a look at one more. If I said to graph we'll call this one g of x. So g of x is equal to the piecewise function 2x minus 3 for x less than 1. Say 5 for x equals 1. And x minus 2 for x greater than 1. And we're going to do the same type of thing. In other words, we're going to split up the domain like they have here and see what happens. So for x less than 1, we know we're going to use y equals, you could say g of x equals, but it's easier to say y equals 2x minus 3. And then remember what I said earlier, you want to test the endpoint no matter what. So the endpoint here is 1, so we're going to, test the endpoint, which would give us y equals 2 times the endpoint, which is 1 minus 3. So 2 times 1 is 2 minus 3. So this equals negative 1. And when you have that, you have to decide, right, do I want this to be an open or a closed circle? Because what this really tells me, right, is that the point I'm using is the x value you subbed in, which is 1, the y value you get out, right, is negative 1. So we have the point 1, negative 1, x comma y, and we're going to use, since there's no equal sign, an open circle. So we have an open circle at 1, negative 1. And if I was to draw this graph here, right, an open circle at 1, negative 1 would put me, here's x value of 1, y value negative 1, we're right here. We're assuming these are all 1 apart. And I'm putting an open circle there. Now remember, this is for the x's less than 1. So if I say, these x's have to be less than 1, I'm talking about values to the left. So this line y equals 2x minus 3 is going to be to the left of this point. Since we have the y equals mx plus b form, I know the y-intercept of negative 3 will be on the graph. And since it's on this side, you know that that y-intercept exists. So the negative 3 would be here. And it's a line, so you could just draw right through it. Additionally, you could just say, the slope is 2. So from point to point, you have to go, up 2 over 1, but you can't go to the right here because our x's have to be less than 1. But you could go, down 2 and to the left 1 and get to the same place. This arrow on the end indicates that we go on forever to the left, covers all the x values, and it goes downward forever. All right, so that's the first piece. The second piece, we talk about when x equals 1. And that tells us that y equals 5. So we know that when x equals 1, y equals 5. That's a point on our graph. So if I'm looking at this, right, 1 is the x value, 1, 2, 3, 4, 5 is the y value. That's the point on my graph. This is a closed circle because we have an equal to in our boundary. So we know we have a closed circle there. Now you don't draw a line in either direction here because it's only for when x equals 1, right? It's not for x is less than 1. It's not for x is greater than 1. It's just when x equals 1. Y equals 5. So that's another point on your graph. And you have that. And then lastly, you want to check the last interval we have, which is when we have x greater than 1. When x is greater than 1, that means we're using y equals x minus 2. And for x greater than 1, remember, you still want to test the endpoint, the boundary point, right? So you want to test the boundary. And the reason you're testing that boundary point is because we still want to know what happens there even though it's not equal. So you got y equals x is 1 minus 2. Well, that equals negative 1. And do we include it? No, because, right, there's no equal sign here. So we have an open circle. At the point, the x value I subbed in is 1. The y value is negative 1. Well, let's go to that on our graph. Well, 1, negative 1 happens to be the one I already have, so it's an open circle that's still there. Now if this had an equal to and it became a closed circle, you'd fill it in. So if you have an open circle and a closed circle on the same point, it automatically becomes closed and you'd fill it in. So I know I'm here, and now for x is greater than 1, I want to follow this line, y equals x minus 2. X is greater than 1 means we want values to the right. This being y equals x minus 2, the y-intercept doesn't really matter to me because the y-intercept isn't to the right of where I have to start from. Right? I'm starting here, going to the right, the y-intercept doesn't come into play. But here the slope, well, the slope is 1 Remember, if the slope is 1, right, the coefficient of x is 1, that means you're going to go from this point up 1 to the right 1, up 1 to the right 1. And so you would draw your line in that way. And so this would be the graph for g of x. So, it looks different. It is a function, right? That's kind of important. G is just the name of this function. It passes the vertical line test. If it didn't pass the vertical line test, then it wouldn't be a function. And that's why it's very important when you're graphing this that you're looking at each of these pieces individually and graphing them in the appropriate part of the graph. So this first part was only for x is less than 1, so I only did it from everything to the left of 1. This second part was for when x equaled 1, so I only did it for that one point. And this last part was for x is greater than 1, so I did it for everything to the right of 1. Remember, you always use the boundary point just to make sure that you know what happens there. An open circle indicates that you're not equal to it there. A closed circle means that you are equal to it there. If it has an equal to in the inequality, you always make it a closed circle on the boundary. So hopefully this helped in refreshing your memory on graphing piecewise functions.